My name is Taran Agnihotri, and today I'll be presenting Lab 4 Circuits and Capacitors. The problem for this lab today is to understand circuits and all their components. These include voltage, current, and resistance, as well as components such as batteries, bulbs, wires, voltmeters, and ammeters. This is made possible by Ohm's law, which states voltage equals current times resistance, or V equals IR, the node rule, in which current flowing in equals the current flowing out, and the loop rule, in which the total potential difference around the loop of a circuit equals 0. In the first part of the experiment, we used the circuit construction kit to create a circuit with two batteries set to 1.5 volts, one resistor set to 100 ohms, one resistor set to 47 ohms, and two ammeters. This can be shown in the pictures below. We predict the current as 0.2 amps, 0.02 amps, and this is the same as our actual current. When we reverse the ammeters, we get the opposite of that, which is negative 0.02 amps. This can be shown below. Continuing, when we replace one ammeter with a voltmeter, the ammeter value is now 0 amps. This is because the circuit is now open and there's no current. The voltmeter value is 3 volts as the potential difference across the circuit is 3 volts. In the third part of the experiment, we replace the voltmeter with a wire, and then we use the voltmeter to measure the potential difference around the closed circuit. As you can see, I have all the values listed out for the points between the circuits. The sum of these measured differences is equal to 0 volts, which is in line with the loop rule. In the fourth part of the experiment, we replace the voltmeter with an ammeter in parallel with a 100 ohm resistor. This changes the current from 0.02 amps to 0.06 amps, as ammeter alters the circuit. The voltmeter previously did not change the circuit, as it has infinite resistance and no current flows through it. As you can see, we can calculate resistance through Ohm's law, and that gives us the resistance of the resistors of 47 ohms and 100 ohms, and the wire as well as the ammeter. These resistances are a bit off because our total amperage is not accurate. In the fifth part of the experiment, we create a circuit with a 9 volt battery, a 10 ohm bulb, and 200 millifarad capacitor in series. The light starts glowing, but eventually fades out. When we disconnect the battery and connect capacitor straight to bulb, the light once again starts glowing, but eventually fades out again. When the battery was connected, the capacitor was charging, and the current in the circuit decreased as it charged. When the battery was disconnected, the capacitor was discharging, and the current in the circuit decreased once again as it discharged. Here are the videos showing the bulb. This first video is when the capacitor is charging. The second video is when the capacitor is discharging. Here are capacitor time calculations. With a 10 ohm bulb, it took 20.04 seconds to fully charge. With a 20 ohm bulb, it took 39.67 seconds to fully charge. As for the discharge times, with a 10 ohm bulb, it took 19.98 seconds, and with a 20 ohm bulb, it took 39.78 seconds. Here are time constant calculations. Theoretically, a plot of the natural log of delta V divided by delta V0 versus time should yield a straight line with a slope of negative 1 over RC. As our slope was negative 0.166, our RC is negative 1 over negative 0.166, which is 6.024 seconds. Theoretically, at 6.024 seconds, the voltage should be 1 over E its original, or 3.31 volts. In our experiment, our circuit construction kit showed 3.334 volts, which is very close. What if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? In real life, an ammeter would have some resistance, which means resistance is not equal to 0 ohms as in the ideal one. It would have slightly changed the overall resistance of the circuit and led to a lower overall current in the circuit. The real currents would have been less than 0.2 amps and 0.6 amps for the respective experimental procedures. What if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? Our ideal model would predict the capacitor reach full charge instantly. However, batteries, wires, and the capacitor all have some internal resistance in real life. The time in real life would not be instant and would take a bit longer as a result of the resistances present in the circuit. In conclusion, we became familiar with the circuits through this experiment. We became familiar with the ideas of voltage, current, and resistance, and the parts of the circuit including batteries, bulbs, wires, voltmeters, and ammeters. This was made possible through Ohm's law, which states voltage equals current times resistance, the node rule, in which current flowing in equals the current flowing out, and the loop rule, in which total potential difference around a loop of a circuit equals 0. With these, we were able to accurately predict resistances, voltage, and current around a circuit. Thank you.